Hello, I'm excited to introduce our work, EcoFuzz, adaptive energy-saving Greybox Fuzzing, as a variant of the Adversarial Multi-Armed Bandit. Our team comes from the National University of Defense Technology, and my name is Taiyue, the first year of doctoral student. As we learn, coverage-based Greybox fuzzing is an effective approach for detecting security vulnerabilities. One typical fuzzer is AFL. For improving AFL, some works focus on the mutation operators such as firefuzz, some focus on the initial seed such as squarefire. However, there are some shortcomings in schedule algorithm of AFL. One is assigned too much energy on high-frequency paths. The energy is the number of fuzzing times assigned to a seed. The other one is that the selected strategy of AFL is simple. Moreover, only few works focus on this direction, such as AFL-fast, and some current models like Markov chain are limited to explain the schedule process more deeply. Therefore, we hope to build a new model for CGF and improve the schedule algorithm of AFL, which contains two parts. The one is search strategy. It tells AFL to select which seed to fuzz. The other one is power schedule. It decides how many energy should be assigned to each seed. In this paper, we make three contributions. First, we process VAMAB to model CGF. Based on this, we develop a tool named EcoFuzz and implement a series of experiments to evaluate. Let's introduce our model. Our model is derived from the classical maps. Supposing there are a constant number of arms, we can do some trials on each arm to get a reward. The probability of playing an arm to get a reward is defined as reward probability. It is constant and unknown in classical math. Our target is maximizing the rewards in infinity trials. For combining the map with CGF, it is natural to regard the arm in map as a seed in CGF, and the reward in CGF is generating a test case to find a new path. However, there are some discrepancy between them. The number of arms and reward probabilities in the classical map are constant. In contrast, they are variable in CGF. Based on this, we process a variant of the adversarial map. In our model, the number of arms is increasing, and the reward probability, which is the probability of a seed to find a new path, is a variable. This is the formula of it. NP stands for the number of total passes, and PIG is the transition of probabilities, which is introduced in Markov chain. From this, we can deduce that the reward probability is decreasing to zero as the number of seeds increasing, which is called probability attenuation. After introducing some important concepts, we explain the trade-off between exploration and exploitation in CGF. Since we didn't know the reward probability of each seed before testing, we need to do some trials on these seeds to estimate their reward probabilities, which is exploration. After that, we select a seed with a high reward probability to test for discovering more paths in a short period. This is exploitation. If we focus on exploring new seeds, CGF may assign fewer energy on the old seeds with high reward probabilities. In contrast, CGF may miss some new seeds with high reward probabilities to find a new path if we focus on testing old seeds. Based on this, we divide the states of CGF into three. First, the initial state, where all seeds are unfuzzed. After testing some seeds, CGF may transfer into exploration state, where part of seeds in the seed queue are fuzzed and some are not. If all seeds in the seed queue are fuzzed, CGF transfers into the exploitation state. According to the three states, we point out how to maximize path coverage in different states. For improving the search strategy, CGF should estimate the reward probabilities of each seed by testing them in the initial and exploration state, and select a seed with high reward probabilities in the exploitation state. For power schedule, it is better for CGF to avoid assigning too much energy on some seed in the exploration state. After explaining our model, we introduce our tool, EcoFuzz. EcoFuzz is based on AFL. In addition, we developed a search strategy called self-transition-based probability estimation method, and developed an adaptive average cost-based power schedule. The states of EcoFuzz are divided into three states. If EcoFuzz in the initial or exploration state, it chooses the next seed to fuzz according to the order of a seed in seed queue. If EcoFuzz is in exploitation state, it chooses the next seed by the search strategy SPEM. After choosing a seed, EcoFuzz assigns energy to the seed by our power schedule algorithm AAPS. Then it mutates the seed and executes the test cases. Now introduce the search strategy and power schedule algorithm in detail. First, the search strategy SPEM. We designed this method for estimating the probabilities. This method is only used to select the seed in the exploitation state. This is the formula of reward probabilities. As PIA is constant, we use its corresponding frequency, FII, as an estimation of it. Then for this part, since it causes attenuation of reward probability, we approximate it as FII divided by the square root of I. Second, the power schedule. We define a crucial concept, average cost. This is the average number of generated test cases to find the path. We use the average cost as a basic line for assigning energy. This is a detailed algorithm. There are three important principles. The first, allocating energy no more than average cost to each seed in the exploration state. Second, less energy is assigned to the seed exercising high-frequency paths. These are validated by the parameter k. In addition, a context adaptive energy allocation mechanism is established. If more energy is allocated than the seed needs to find a path, EcoFuzz assigns less energy in the next time by reducing the rate. Finally, we introduce our evaluation. We evaluate EcoFuzz on 14 programs and compare it with 7 tools, each case for 24 hours and repeat for 5 times. The evaluation metric include path coverage, number of test cases, and average cost. The black line stands for EcoFuzz. From this picture, EcoFuzz performs best on most programs with the highest path coverage in the least executions. From this table, EcoFuzz outperforms other tools on average cost. For example, compared to AFL, EcoFuzz finds 214% of the path coverage and generates only 68% test case, while reducing 55% average cost. We also evaluate our schedule algorithm by choosing each best performance of EcoFuzz, fragile AFL, FairFuzz, and EcoFuzz field on fuzzy. We record the energy allocated in random stages of each turns and the consumed energy for discovering the newest path of each turns. We also record the frequency of allocations with finding new paths of the seed in the exploitation state. Then we define the evaluation metric, which includes the utilization ratio of energy, the average utilization ratio, and the frequency of effective allocation. This is a scatter map of the utilization ratio in the fuzzing process. From this, the ratios of most points in fragile AFL and AFL new are under 1.5. However, they are more closer to 1.0 in EcoFuzz. Moreover, from the tables, EcoFuzz promotes the best with the least average cost, highest average utilization, highest frequency of effective allocation, and highest ratios, which proves that the search strategy and power schedule of EcoFuzz are efficient. EcoFuzz is also efficient in detecting vulnerabilities, with finding 12 vulnerabilities and getting 2 CVEs. In conclusion, in this paper, we process a VAMAB to model the schedule process of CGF and explain the trade-off between the exploration and exploitation in CGF. Most importantly, our model point out how to improve Greybox fuzzing. First, improving the reward probability of each seed. Second, establishing the mechanism of evaluating the seeds. Third, optimizing the power schedule. Based on this model, we developed a tool named EcoFuzz. EcoFuzz implements a new search strategy to estimate the reward probabilities of seeds and select the high reward probability seeds in the exploitation stage. We also develop an adaptive energy average cost-based power schedule to attain energy. Finally, we evaluate EcoFuzz. EcoFuzz can attain 214% of the path cavity of effort and reducing 32% test cases generation. EcoFuzz also identified 12 vulnerabilities with 2 CVEs, which have been proved as an efficient tool. Thank you for your listening. If you have any questions about our work, welcome to contact us.